Our next guest is Dennis van Puyvelde. Dennis is a little closer to home and even in the same time zone as us. He's joining us from Canberra, where he works as the head of renewable gas at Energy Networks Australia. Dennis is responsible for work programs and strategy projects for the Gas Committee and its related technical, marketing and policy reference groups. Dennis has over 20 years experience in the energy sector, with particular emphasis on low emission technologies, including gasification, biogas, carbon capture and storage, and hydrogen. He has a PhD and an honours degree in chemical engineering and a graduate certificate in public sector leadership. Dennis will be speaking to us today on his vision for a pathway to net zero. Dennis, welcome to the forum. Over to you.
Thank you, Kiralee. Thanks for the introduction. So I'd really like to talk about the pathway to net zero and the impact on customers. So I'll just take this off. No, wait. So as Kiralee said, I'm the head of renewable gas with Energy Networks Australia. Energy Networks Australia is the industry association for gas distribution networks and for electricity transmission and electricity distribution networks. My head office is based in Melbourne, but we've got people in Canberra, in Brisbane and in Perth as well. So we're a national organisation. So what I'd like to talk about today is the need for global emission reductions. So I think there's a common understanding that we need to reduce emissions across the globe to avoid climate change. In 2015, there was an agreement made, a global agreement made in Paris to limit global warming to 2 degrees. And there was also an additional focus on setting the limit to 1.5 degrees. What that implied was that countries made commitments to reach peak emissions as soon as possible. And they also would then achieve net zero emissions in the second half of the century. Australia signed up at that point and set a target of 26 to 28% emission reductions by 2030. And since then, at the agreement, at the last meeting in Glasgow, just last year, they've actually also set an agreement to reach net zero emissions by 2050. All Australian states and territories have also adopted this target, and some have adopted interim targets. For example, Victoria's now got a 50% emission reduction target by 2030. So I'd like to spend a few minutes to talk about what does that actually mean in an Australian context from an emissions perspective. So this is the data from the Commonwealth Government. This is Australia's emissions projections at 2030. What this shows is that emissions have already reduced by around 20% from the 2005 level. So generally, emission reductions are taken from the 2005 level. Most of those emission reductions have come from changes in the land use sector, from land use change and from forestry. So that's where most of the current emission reductions have come from. In the next decade, from 2020 to 2030, there'll be more emission reductions at a rate of around 8 million tonnes per year. Most of that will actually come from the electricity sector. It's interesting to note that the electricity sector will reach around 50% of its emissions by 2030, and that will be will be achieved mainly through renewable energy, mostly through installing rooftop PV. On that journey, we've only just started that journey of reducing emissions from electricity. Currently, we're probably around 20% lower than what we were 2005 value. So we need to do a lot more work to get to that 50% reduction by 2030, sorry. The other sectors, such as agriculture, fugitive emissions, transport, gas, and so forth, there hasn't been a lot of change, or there's not a lot of change in this decade, but they've actually grown since that 2005 level. So there's a lot of growth in emissions from transport, emissions from extra gas use, emissions from fugitive emissions, mainly related to LNG exports. So when you extrapolate this to 2050, it actually shows that the amount of effort you need to do is roughly 3 times as much as what we'll be doing this decade so 3 times as much each year. But we also need to do a lot more effort in those other sectors, which we haven't really started yet. So there's also discussion about trying to reach net zero emission by 2035, and that means the amount of effort is even greater. So that's a great ambition to try and reach the net zero by 2035 in line with that 1.5 degree temperature increase, but that requires huge amounts of effort. So I'm just highlighting this just to emphasise that this is a massive task. This is a task that requires contributions from each sector of the economy. And within the energy sector, we've only just really started on that. So we've only just started on that from an electricity perspective in terms of renewable electricity, which, as I mentioned, is currently only contributing 30% of the total electricity mix. So there's a lot of work to be done. So I'd like to talk about what the role of renewable and decarbonised gas is to help us achieve these emission reduction targets. So in 2015, we produced a report called Gas Vision 2050. So this was a report that was developed across the gas industry. So it included the upstream gas producers, pipeline and distribution networks, appliance manufacturers. It was a document in response to the Paris Agreement on climate change. So this outlined how transformational technologies would be deployed to reach net zero emissions from using gaseous fuels in Australia. So there's 4 pathways of reducing emissions from gas use. I'll briefly talk about some of these. I'll then talk about decarbonising the fuel in more detail. So energy efficiency is a technology that's quite very well known. It's basically trying to replace existing appliances with more efficient appliances. We're also upgrading homes, for example, with more efficient homes, so increasing the insulation. Closing your window, closing your curtains at night is also a good way of increasing energy efficiency. So that's actually in some ways, a low cost strategy of reducing emissions, because if you don't use the energy, you don't produce emissions associated with it. On the right-hand side, I've got carbon offsets. Now, once again, that's something that's currently available. It's quite easy to purchase carbon offsets. Most of the major electricity and gas retailers offer carbon offsets on their products. So you can already have net zero energy at the moment. There's also an option of electrifying heat. There's homes in Australia that are fully electrified. So there's around 50% of homes that are on the gas connection, and another 20% of homes that have a connection to bottled gas. So combined, that's around 70%. But there's another 30% of homes that don't actually have gas. So there are technologies available where you can use electrified solutions. I'll talk a bit more about that later, because that's probably not very suitable where gas networks are due to the higher levels of gas needed to provide heating. Then I'd like to talk more about the decarbonising the fuel, which is basically through transformational technologies, such as these. So there's 4 transformation technologies we identified in Gas Vision 2050. One is the use of hydrogen. The other one is biogas, and renewable methane are actually very similar. I'll talk about that as well. And then there's carbon capture and storage. Won't focus so much on carbon capture and storage. That's more a technology upstream for reducing emissions from industrial processes, from gas production and from power generation. Focus more on the other technologies which provide emission-free gas that can continue to be used. So we're on a journey to convert networks to actually produce and transport renewable gas by 2050. So when we outlined our original document, we've thought the next 5 years from 2017 up until the early 2020s is really about beginning or doing more innovation and demonstrating projects. I'll show in the next slide how we progress in that. Then in the next 5 to 10 years, probably towards the end of this decade, say, we'll be looking at reducing emissions by blending biogas and hydrogen in gas networks, so that replaces part of the natural gas with a renewable gas product, and that lowers the emissions. Then in the longer term, fully converting to that emission-free biogas or hydrogen. So this slide shows how we've already progressed that, how industry has already progressed that. So there are a number of projects already operational. This slide I could probably talk to for 15 minutes, but I won't. So I'll just briefly highlight that there are projects operational. There are projects operational in Adelaide, in Western Sydney, that are already injecting hydrogen into the network. So customers are already receiving a small blend of hydrogen in their network. There's also plans to for new projects to blend hydrogen into industrial precincts, and plans for larger scale projects where hydrogen can be blended into whole towns. So I'd like to talk a bit about the different pathways of producing renewable gas. So this diagram shows how renewable methane can be produced. There are two general pathways. One's using the organic waste. So for example, landfill waste or organic waste, such as food scraps from the house, that can be put into a biodigester, which then produces methane and a few other gases. So once that's cleaned up, it produces biomethane. That biomethane can be directly injected into the network once it's cleaned up to network specifications, and it basically works the same as natural gas. On the lower part of the diagram shows a synthetic renewable methane pathway, which looks at using hydrogen, reacting that with carbon dioxide absorbed from the air, and then that also produces renewable methane, which similarly can be injected into pipelines and networks, and it works the same as natural gas. One of the main challenges with biomethane is the resource potential. There's a lot of uncertainty of how much resource is available to produce biomethane and how easily it can be collected. Some of the feedstocks include organic wastes, agricultural waste, forestry waste. There's also discussion about energy crops, where crops are grown for the sole purpose of producing bioenergy. There's a high level of uncertainty in the estimates of how much of this resource is available. But a recent report by ARENA, their bioenergy roadmap, showed that there's 2,600 petajoules of theoretical resource potential. And they saw that that could possibly produce 33% of gas in networks by 2050. And just as a reference point, the gas in networks for residential consumption across the country is 166 petajoules. So when you compare those two numbers, you would say there's an awful lot of potential, but there's also an awful lot of uncertainty in that 2,600 petajoules and whether it is accessible or not. And that's why I mentioned on the previous slide the synthetic renewable methane, because that's another pathway that can provide that renewable methane. The cost competitiveness is one of the challenges for biomethane. As you can see on the green bar, that's the cost of biomethane just by itself from organic matter. Even in that case, this is based on research from Future Fuel CRC. The production cost depends on its location and how much of the biomass is collected in a single area. So if you look at the different plant configuration, having a single plant, you can achieve massive cost reductions to having smaller distributed plants across the country. There are also options in terms of revenue of, there's in biomethane process, you produce fertilizer, and you also avoid depositing the waste in landfill. So there's some revenue options. There's also policy options, and they've been deployed quite readily in the UK and in Europe. And by a combination of all those different configurations, we're able to get to a competitive price for biomethane compared to the Sydney gate price for natural gas. So that's provides a lot of opportunity there. So what are some of the implications for customers for biomethane, biorenewable methane? It's a net zero emissions gas, and it's basically the same as natural gas. So it can continue to be used. You can continue to use the same appliances and have the same experience. There is uncertainty around the availability, but that can be supplemented by synthetic renewable methane. And there's also some discussion about what's the competition for this resource? Will it possibly end up in a higher value sector, for example, aviation? There are opportunities to reduce costs to become competitive with natural gas. But at the moment, one of the main limiting factors for customers is that there's no market for renewable gas at the moment. There's a lot of demand for customers who want renewable gas. There's people who want to supply renewable gas, but there's still no market at the moment. So it's something that we need to work on. Now I'd like to turn my attention to renewable hydrogen. So this pathway here really shows that hydrogen can be produced from renewable electricity. It splits basically water from an electrolyzer. So you apply renewable electricity to water in an electrolyzer that produces hydrogen atoms and oxygen atoms. Those hydrogen atoms are captured and they're then compressed, and they can be used as a replacement for gas. Hydrogen has a broad range of uses, and I've got another slide coming up which shows that. It can also be produced from other sources of other energy sources, for example, natural gas with carbon capture and storage. And there's a whole rainbow of colours of hydrogen that identify the different sources it can come from. But the main thing is the hydrogen that's produced is emission-free. So when it's used and burnt, it doesn't produce any carbon dioxide emissions. This is that slide I was talking about with all the different applications. So it can be used as an industry feedstock in industry as heat and power, for heat and power in buildings, and also has a big role in the transport sector. So it has a very, very big role across the economy, and there's quite a number of projections out there that show that the final energy demand in 2050 or so for hydrogen will be around 20 or 25% of the global energy demand. Once again, cost is an issue at the moment. So currently, green hydrogen costs more than natural gas. Actually, grey hydrogen produced from natural gas also costs more than natural gas. That's not quite competitive at the moment. There's a lot of work. I showed you a previous slide where networks are already investing in deploying hydrogen projects. And that work, as combined with research across the world, is actually leading to major cost reductions in hydrogen. So by 2050, we'll see that green hydrogen becomes cost competitive with grey hydrogen. What this also means is that actually hydrogen is competitive in some instances, for example, return to base vehicles. But for residential consumption, it's not quite competitive yet. So this is some data from the Clean Energy Finance Corporation, which shows that the price gap between hydrogen and natural gas in 2020 is $1.50. That narrows to about 10 cents per kilogram in 2030, and in the early 2030s, it levels out. And by 2050, it shows that hydrogen is competitive as a fuel for replacing gas. Now, one of the things with hydrogen is that it behaves slightly differently to natural gas. So there's a role where we need to convert networks, and that's where there's some implications for customers. So this is a conceptual pathway of how we convert networks across the country. So from 2020 onwards, we can start blending hydrogen up to 10 or 20%. Appliances and still work at that level. They work safely and effectively at that level, so that's no concerns. Then there's a point where we need to convert a set part of the networks to 100% hydrogen. That will require appliance modification and a planned program to make sure that those appliances are converted in a safe and effective manner. A lot of the networks in Australia, the gas networks, have already upgraded as part of their mains replacement program. So that's really replacing their networks from the old cast iron pipes to new plastic pipes. And those pipes are actually capable of transporting hydrogen safely. So a lot of that work has already been done. There is also, we can draw on previous experiences in converting the network. Going back to the late 60s, Australia's gas used to be Towns gas, which was basically produced from coal. The discoveries of natural gas in the mid-1960s provided this as a product to the market. So through that process of the replacement program, it was about a 12-year program where households were converted across the country to move from Towns gas to natural gas. So, we have done this before. It was 50 years ago. I'm sure the social environment and customers were quite different 50 years ago, but that's something that we need to work with. Appliances for hydrogen do exist. There's demonstration projects in the UK where they've got appliances working, where they've got cooktops working, where they've got boilers, where they've got hot water heating systems and so forth. So there are appliances on the way, but they aren't commercially available yet. This is just an example of a plan that the UK has developed of how they can convert all their natural gas connections to hydrogen. As you can see, it takes to convert 15 million meter points takes quite a number of years. They've phased this as doing one region at a time, just to allow both build-up of hydrogen production and then to focus on different regions to convert that from natural gas to hydrogen. So this is a long-term journey. Similarly, we've done work in Australia to look at what we need to do from a network to decarbonise. We've produced this plan which looks at blending hydrogen up to 10 or 20% across the network by 2030s. Then looking at demonstrating 100% hydrogen town or region before 2030, then converting to 100% between 2030 and 2050 or earlier. So this is a national plan. Each one of our gas distribution networks has a more detailed version of that, or is working on a more detailed version of that with slightly different ambitions, but this is roughly a plan to identify how we can reach net zero from gas use networks. So what's the impacts for customers? So no changes really for blending hydrogen. So in the next 5 or 10 years, when we introduce a blend, there's no changes. After that, there's a need for a planned conversion to convert to 100% hydrogen, which might produce a slightly different experience for customers. Hydrogen is, as I mentioned, is a different fuel. It burns slightly differently. So there might be some slight changes, although a lot of the appliances that have been built today operate the same as existing appliances. Supportive policy can minimise disruption. And by that, I mean, especially from an appliance side, if there's a mandate to, say, introduce dual fuel appliances that minimise the conversion process, that makes the process easier for customers when that conversion happens. There's data out there that says it becomes cost competitive with that gas in the 2030s. But once again, we don't really have a market for renewable gas. So that's something that we need to work on. So the question is, one of the questions, there's lots of questions. Biomethane and hydrogen, what's best for customers? I don't really have an answer to this yet. I think there's a role for both. I think there's a role in the near term. I think biomethane has an important role. In the longer term, hydrogen may have a more important role. I think it also depends on the different regions. In some regions, some agricultural regions, for example, away from a gas network, building a biomethane facility and servicing a local community may work better, and hydrogen may play a bigger role in converting states, for example, the whole state of Victoria to replace their gas use. So it's really, there's not really a single best answer. It all depends on the demand, on resource availability, on cost, on the speed of transition, and also on the other resource demands. So I was just going to quickly talk about the benefits of renewable gas networks. And also, in some ways, I thought this also addresses the question of why not just electrify? Because there's been a lot of discussion of maybe we should just electrify. So I brought this down from 10 points to 5. I'll just quickly run through them. Basically, gas is used It's got lots of benefits. It's used across the whole country in a whole lot of different sectors. Being able to, some of these things you cannot electrify. For example, industrial feedstocks cannot be electrified. You can't really electrify exports. It's difficult to electrify residential and commercial heating. So by continuing to use a gaseous fuel, you'd be able to continue servicing all these different sectors. Related to this is the second point, which is gas infrastructure is there to meet heating load. It's purposely built, actually. This is the Victorian heat load. As you can see, there's a massive heat load in winter. During the winter periods, that's the light blue chart. And the gas infrastructure and the storage infrastructure associated with that is actually built to meet that heating load. So it's not easy to replace that. When you introduce hydrogen, you actually increase your utilization of grid-connected renewables. There's already a large amount of renewables that's curtailed. So by being able to use that electricity, you can convert that to hydrogen, which creates a high utilization of that renewable energy generation. Then you can also use that hydrogen in your networks. This is some other research with Future Fuel CRC that looked at the emissions when you electrify too quickly. If you electrify too quickly, you end up replacing a lot of your gas that you use directly with peaking gas load. And the result is that, and it also happens at night and in the colder parts when there's lower levels of renewable generation available. The implication is that if you push electrification too fast, it may actually increase emissions in the short term. So, and lastly, some work we've done with Frontier Economics shows that when you look at the whole gas sector, the whole gas industry as a whole, using a renewable fuel such as hydrogen is cheaper than full electrification, and it's by a factor of about it's about half the cost. And for Victoria, it actually was only 41%. At the cost of hydrogen to replace natural gas is around 41% of the cost of electrifying the state. There's a lot of debate around this, a lot of discussion, lots of assumptions, but I think it's a really key point to keep in mind. So the role of policy, I think there's policy is really there to help support technology projects, help really identify the resource potential for biomethane. And as I mentioned, there's no market yet, so it's really there to enable market mechanisms, looking at renewable gas targets, for example, reverse auctions, but also to support that local appliance industry to build capacity to provide hydrogen appliances. So just to summarise, reaching net zero requires action across the whole economy. This will impact customers in many ways. I've only raised a few this morning, and I'm sure there's many more that we can identify. Renewable gas provides an option to decarbonise, and blending hydrogen in networks offers a lower cost opportunity to scale up hydrogen production supply. We're already doing work. The gas networks are already demonstrating the role of renewable gas. We'll continue to do so, and there's supportive policies can minimise the disruption. So just before I finish up, I just want to do a blatant plug for our. We've got if you want to hear more about renewable gas and electricity and networks and so forth, we've got a conference coming up in Brisbane on the 16th to 18th of March. It's actually been quite popular. We've had a lot of response to it already. So if you're interested in attending our conference, please come and join us. And with that, I'll hand back to Kiralee.